Welcome anybody. What I have here today is a time test of some assembly code, a module that I wrote a year or two ago versus an assembly module I've just written recently. The test is going to compare object-oriented programming versus data designed or data-oriented programming, so to speak. This concept is not new. There's many videos about it on YouTube. It has to do with aligning your data up consecutively in memory so that you hit the cache, don't have cache misses, you have cache hits, and it enables SIMD. And we'll do some SIMD in this video as well. So what I would like to talk about first with my little visual aid here is the way, this is the control version of the test, which is the code that I wrote a few years ago, and this is essentially how it's called mixed collection module operates. So what you see is this top row here. This represents, oops, don't want that. This represents, it's an array of pointers is what it is. This is how the mixed collection works. And each pointer points to somewhere in memory, which is an object. And the memory manager hands out chunks of memory for the mixed collection module to use. So what we have is pointers to somewhere in memory. Now, initially, like in this test, this memory will actually be contiguous with some headers. So it's not really out of order, actually. But as time goes on and you add and delete, and it can be out of order. It can be in any order of memory. So this represents how it's currently working my control test. And this represents the new version that I've been working on. This is going to be the data-oriented design. So what we have is what I would call an array of structs. So the array will be one continuous array it's malloc, memory allocation. It doesn't use the same memory manager. It just kind of goes directly to the operating system and says, give me a chunk of memory this big. Within that chunk of memory is going to be struct. It's going to be all the items of the object items. Now, the x coordinate, though, still isn't contiguous because the x, it goes x, y, vx, vy, health, x. So the x's aren't contiguous. But this x is actually a pointer. And down here is another array that has all the x values that are contiguous. Likewise, the y coordinate is a pointer that points to an array down here of all the contiguous y coordinates. So let's go to the code a second. Well, let's see here. So when the SIMD, I'll just talk about one more thing. So when the SIMD runs, it doesn't move from record to record to record to record to 1, 2, 3, 4, 5. What it does is it has special access of where is the address of the first x coordinate and where is the address of the very last x coordinate. It'll literally set up a SIMD loop to read in the x values into the SIMD registers from this contiguous memory, thus bypassing the move first, move next, move previous movements. Now and that's what's done to calculate the new x and y coordinates. So what the calculation is going to be is it's going to be just one simple addition in the test. It's going to take x plus the velocity of x. And we're kind of assuming that the velocity of x was multiplied by a time, and we ended up with a value there. That's all not part of the simulation. The simulation is really just one addition. It's kind of a simplified version. So let's go take a look at the assembly. This module here is what I call the normal entity. This is done in the control test. This is your struct we're looking at, the x, y, vx, vy, the health. It also has a name, so it's not really a very efficient entity. It's got this big string object in here. It also has this buffer with a string at the top. So it's not really a very efficient object, let's say. And then there was one function called echo where it just prints out its values. Now, the SIMD entity looks the same, except the x coordinate has this SIMD keyword, and it's a pointer. Now the SIMD keyword is something I had to make brand new for this project, and I really didn't know what to call it, so I called it SIMD. And what the compiler does with that is it kind of bag it and tag it. It doesn't really do anything except document it that it's there, and then there is a way for a runtime execution code to then iterate through the variables in this module and then siphon out which variables have the SIMD keyword in it. And that is kind of all built into the SIMD collection object or module that I've written. So all you really need to do is just tag which ones you want to use for SIMD, and it'll do the rest for you. So let's take a look at the program here. Let's go to the top. What I'm going to do is I'm going to divide the simulation or the test into 3 different times. The time to create the objects, the time to run the simulation, and then the time to deallocate. The reason I want to do that is because I want to separate the create and the deallocate out, because those kind of happen maybe only once or just a few times, whereas the actually calculating of the coordinates could happen in every single iteration of a game loop, and it's something that happens more frequently. So I want that to be separated out. So it's three times per test. Now I'm just gonna run through this here. This is start new test. What's the number of entities? So it's going to ask for how many entities. So we can go. I ran it to even 1 million, and it still ran, although it took a little bit of time. Number of iterations. So that'll be taking the same entity and calculating it multiple times. So let's go here. So test 2A is going to be the control test. That's going to run. That's going to echo out the times. That's going to run test 2B. That's the SIMD test. It's going to echo out the times. And then let's do some calculation of percentages. And you know what? How about let's just run the program. See what we got. If you want to see more, you can see more. Number of entities. All right, let's do 100,000. Number of iterations. Let's go 100. Okay, so you can see here that test 2A, those are clock ticks of the CPU in decimal form. Test 2B has clock ticks of the CPU in decimal form. Now the percentages down here show the create percentage at 3.34%, which means the new version took 3% of the time, which is quite a bit faster to create the objects. And typically that's because it's in an array and the memory's only asked for once, and whereas the other one has to ask the memory allocator 100,000 times for a new object. Oops, I lost my window. The run simulation was at 1% of the time, which is about 100 times faster, which is kind of jaw-dropping. I'm shocked. Now, either that proves that the data-oriented design is very fast, or it proves that the other design is very slow. It depends on how you look at it. But it's definitely 100 times faster, and I had no idea it was going to be that much faster. The deallocate was extremely fast. It was 0.12% of the time. Let's kind of do it again. Let's go 100,000 again. Let's go 1,000 iterations. You see there's some delay there for the first test, but then the second test, blink. So you can actually see, and then it actually nailed 1%. So there's actually 100 times faster. You can actually see the difference there. We had a pause for the first test to run. The second test was just blink, 0 to exit. So let's go back here. Let's take a quick look at test 2A. It uses the mixed collection. Starts my timer, resets the timer, starts the timer, creates a loop or does an open on the collection, starts a do loop to create the entities, stops the timer, records it as time to create. So run the simulation, do a move first, that in there. It's going to add the velocity of x to x, add the velocity of y to y, move to the next entity. So it's a loop to it's a double loop because it does the iterations, right? So it does each object, and the next iteration will be like another iteration of the game loop. Stop that, and then there's a verify, which I'm not posting the verify results yet. I should have done that before to prove the numbers, but I know the loops are running, so that's what's most important. And then there's the deallocate, remove all. Test 2B uses a different collection object. It's called the SIMD collection module, and it's got some more variables here. We won't look at those too much. It's not too much bigger, though. It's not too much more coding. This calculate alignment padding, not really necessary. I was doing that for debugging. It basically kind of opens the collection. There's a little more to what the collection can do. It can do multiple lists in the array, but in this run we're just doing one list, one array. Well, it's all one array, but it's just one list inside one array. Then it goes through and makes a do loop and adds the item, records initial values for the x and y, stops the clock, starts the next clock. Now the simulation, here's where it's not going to do a move next throughout the collection. It runs a function called getRange, and you can see the variable it's asking for, the x, y, vx, vy. So what it does is it moves the starting address into these registers, address of x, address of y, and those are basically going to be R10, R11, R12, R13. And it starts this SIMD loop where it moves the contents at the address of x into XMM1 and moves VX and XM2, and it does this add of XMM1 and XMM2, and then it takes the result and just moves it back in memory. Now each iteration of this loop is 16. 16 byte register, 2 bytes per value, so it's 8 additions. Again, then it does the Y coordinate, same steps. Now it adds to the address 16 bytes for the next iteration of the loop. One thing also that the object does, when you ask for how many elements you want in the array, it's going to pad it out for you and give you extra elements, so that your last iteration of the loop is just adding zeros and not jumping off into someone else's memory. So there are some concerns when doing this, or to make sure things get done right. Then stop the clock, record the time, do a verify, the deallocate, and that's basically it. So the beauty of it is that, again, with the get range function, you access these arrays directly. So you get the benefit of having data oriented design programming, but you also get the benefits of object-oriented programming. So you get both, and that's what I like, because I like object-oriented programming. I love the abstractions of it, and I like to use it, but I also really desire the performance of running SIMD as well, and now I can do that, and it's all built into this SIMD collection, and there it is. I guess that's all I got to say. Thanks for watching.